Okay, so let's take a look at part B, and hopefully you got the same thing I did, and if you got stuck at any point, well, that's good. That's the first part. First step towards getting it figured out is getting stuck first. So we'll clear things up by working through it now. So just because the function was defined on the previous page, we've got, I'll just write it down here, we've got g of x is x cubed minus 6x squared plus 5, and the interval we'll use is -3 to 5. So that was the interval we were given. So step one, find the critical numbers. So take your derivative right off the bat, because we need it to find the critical numbers. So you use the power rule on each term here. You're going to get 3x squared minus 12x, and we want to find out where that is equal to 0 or undefined. Right? That's how we're going to find the critical numbers. And since this is a polynomial, it's defined everywhere, so there won't be any type 2 critical numbers, just like our previous example. So we're going to need to, but we are going to look for type 1, pardon me, we are going to look for type 1 critical numbers. So figure out when g prime of x is equal to 0. So factor out everything you can, and this actually we can pull out a 3x here, so we're going to get 3x times x minus 4. And then that, right away, it's factored nicely. It tells you the critical numbers. So g prime of x is equal to 0 when x is either equal to 0 or 4. So just like in the previous example, let's make a point of highlighting this as our critical numbers. And they're both type 1. Okay, so that's step 1, complete. Step 2, evaluate the function at every critical number. Got it right here, right? So we found all the critical numbers in step 1. Our function is called g, not f in this case. So step 2, evaluate the function. In our case, it's g at each critical number. So we'll plug these critical numbers in. So g of 0, plug 0 in, you're going to get 0 cubed minus 6 times 0 squared plus 5. That just works out to 5. And then g of 4, well, what's g of 4? 4 cubed minus 6 times 4 squared plus 5. So what does that work out to be? 4 cubed, 4 times 4 is 16, times 4 again is 64. So that will be 64 minus, and then this will be 6 times 4 squared. 4 squared is 16. So 6 times 16 ends up being 96. So you've actually got 64 minus 96 plus 5, and that 64 minus 96 is negative 32. So then when you add 5, you'll get negative 27. So that's the value that corresponds to 4. Now, step 3, evaluate the function at each of the endpoints, right? We want to evaluate, here it's f of a and f of b in general, but in our case, we want to evaluate g of -3 and g of positive 5. So g of -3, we're going to get -3 cubed minus 6 times -3 squared plus 5. So 3 squared, or 3 cubed is 27, but it's negative. So we're going to get negative 27. Here it's 3 squared. -3 squared is 9. So you got -6 times 9, which is -54. And then plus 5. So 27 added to 54, that's going to give you 81. But they're both negative, so it's -81. If you add 5, you're going to get -76. So that's g of -3, and then our last one is g of 5. So we're going to get, for that one, we'll get 5 to the power of 3 minus 6 times 5 squared plus 5. So what does that work out to be? 5 cubed, that's 5 times 5 is 25. 5 quarters is $1.25, right? So this is 5 cubed is actually 125. And then here we've got 6 times 5 squared. 5 squared again is 25. 6 times 25, 6 quarters would be $1.50. So that's minus 150. And then we got plus 5 at the end. All right, well then 125 minus 150, that'll leave you in the whole 25. So we are -25 plus 20 is plus 5 is -20. So that's what we get for 5. So our list of values that we formed We got -5, pardon me, +5, -27, -76, and -20. So, well, largest one, or the greatest value, is actually 5, +5. That's your absolute maximum. And then your absolute minimum is the least value, which is -76. So to finish this off, let's just say, therefore, g of 0 equals 5 is the absolute maximum. Let's just say this is the absolute max. You just abbreviate absolute with just ABS if you like. And then for our minimum value, well, what was it? -76 was our least value. So g of -3 is equal to -76 is the absolute minimum. Okay, so that's all there is to it for applying the extreme value theorem. Of course, sometimes finding the critical numbers for some functions is a little bit harder, right? In both of these examples, the derivative, well, let me back up. In both of these examples, the functions themselves were polynomials, so the derivatives were also polynomials. We had no type 2 critical numbers, and to find the critical numbers, we just had to factor, and that was all. That was basically a one-step process. So for both of these examples, I'll confess, I did pick ones that didn't have too many difficulties in finding critical numbers, but in general they can be a little bit trickier. So it's important to tackle the suggested exercises to make sure you get exposed to the tougher problems as well. One last comment. What about local mins and local maxes? Does this method give you the local extrema as well? I mean, technically in a twisted sense it does, because you're going to get local extrema. You're going to pick them up along the way when you build your list in step 2 and step 3. The only thing is, for example, -20 and -27, you don't know for sure that those are either local mins or local maxes. You don't know that for sure, but you do know if there were any other local mins and local maxes, then they would be included in -20. Like -27 and -20 would be the candidates, right? So it narrows it down, but it doesn't give you only positive information, in the sense that you don't know now, without looking at the graph or getting some other information some other way, you don't know if -27 is a local minimum, a local maximum, or neither. And same with -20. The only thing we know for sure is that 5 is the absolute max, -76 is the absolute min, and that if there are any local mins or maxes, the only possibilities are -27 and -20. Right? So that's all you really know.